Hi, I'm Haosen from University of Rochester. Today, we are presenting our work on building fast recoverable persistent data structures. This paper is co-authored by me, Wentao Cai, Mingzhe Du, Louis Jenkins, Benjamin Valpey, and Michael Scott. Non-volatile byte-addressable memory offers the possibility of keeping pointer-rich data structures across program runs and even crashes. Given that CPU caches are still volatile though, we need explicit write-back and fence instructions to make sure operations are persisted in the correct order. Durable linearizability is the most intuitive and widely used correctness criterion for persistent data structures, but it incurs high latency in every operation. For example, each write operation can only return when all of its updates to objects on NVM are persisted. The buffered version of durable linearizability has the potential to reduce the latency on persistence ordering, but currently, all the existing implementations of buffered durable linearizability are not general. In this paper, we propose Montage, the first general system that helps building buffered durably linearizable data structures. It persists operations at the granularity of coarse-grained epochs. Such epochs typically have lengths somewhere between 1 and 10 milliseconds for optimal performance. Operations can also be immediately persisted with a sync call, which is a commonly used persistence model by database or file systems when they perform I/O operations. In the current implementation, two most recent epochs may be lost on a crash, as described later on in this talk. It also further reduces the cost of persistence by only putting abstraction-related data in NVM, and metadata that are rebutable from those abstract data will be recovered after a crash. Let's start with introducing rules of persist ordering. As an intuitive and widely used correctness criterion, durable linearizability requires operations to persist before the return. This gives us the strongest recoverability, in the sense that in the wake of a crash, data structures can be recovered to the last finished operation before the crash. But the downside is that writes back and fences are issued to wait for all updates to NVM to finish before their corresponding operations return, which can be quite expensive. Sometimes, however, we don't need persistence orders as strong as required by durable linearizability, especially when an application can tolerate some progress loss on a crash, or when the application has specific points in its execution where it needs to know that all previous operations are persisted, just like what databases and file systems would do before I/O to persistent storage. In such cases, buffer durable linearizability poses weaker ordering constraints, which can lower the overhead on ordering. It only requires that operations do not persist in an order in opposite to their happens before order. For example, if O1 happens before O2, O1 should never be persisted after O2, but they can be persisted at the same time. This gives us the benefit that an operation can return without persisting, hence avoiding the need to wait for persistence on every operation. Inspired by DALI, the first practice of buffer durable linearizability, Montage implements buffer durable linearizability by dividing time into epochs, which marks the persistence order of operations in batches. If two operations are ordered by epoch, they either do not have happens before order, or their happens before order is consistent with epoch order. Montage makes sure that each operation is marked with only one epoch, and operations in the same epoch persist atomically together. The epoch-based periodic persistence system of Montage is designed as follows. All write operations are assigned epoch numbers, which is read from a persistent slow-ticking epoch clock. In one write operation, all the writes to persistent blocks are marked with the same epoch number, so operations are linearized with epoch boundaries. This is important because the data structure is persisted in the granularity of epochs. If some updates of an operation are marked with a different epoch, the operation is not guaranteed to be failure atomic. Also, although an operation may return after a new epoch starts, it needs to be seen as linearized in the epoch of its payloads. Since read-only operations has nothing to persist, they don't need epoch numbers, but they are still linearized with other operations, and they can always find an epoch to linearize in. Before the epoch boundary from E to E+1, all operations in epoch E-1 are weighted to finish and persist. If a crash happens in epoch E, the history will be driven back to the end of epoch E-2. All operations in E-1 and E are discarded. Consequently, for those blocks last updated in previous epochs, they cannot be in-place updated in the new epoch because the history of those blocks in old epochs needs to be preserved just in case the new epoch is discarded. Instead, they make new copies of those blocks and update the new copies. During this process, the data structure needs to make sure that the linearization order of operations is consistent with their epoch number. Specifically, if an operation sees some block from a later epoch, there might be an ordering issue. For example, as W1 and W6 overlap in time, it might be possible for W1 to linearize after W6, which is inconsistent with their epoch order. In such cases, Montage can optionally raise an exception as a reminder. Note that this issue is not necessarily faulty depending on the data structures. For example, helping and cleanup operations among non-blocking data structures may update or reclaim some payloads. Out-of-order persistence of those operations may not be an issue since they do not affect the abstract state of the data structures. Montage further reduces persistence overhead by reducing the amount of persistent data. Prior works like non-blocking persistent memory allocator RALOC, persistent data structure implementations like NV-Tree, FP-Tree, and Pronto showed that after crashes, data structures can be rebuilt from a set of data representing its abstraction. For example, the abstract data of sets and mappings can be their keys and values. For queues, it can be their values and queue node orders. For graphs, it can be vertices and edges together with their relationships. Montage allows data structures to only persist those data and help iterate through those abstract data during recovery, so the transient indexing can be rebuilt. For a mapping, for example, this can be a linked list, a hash map, or a tree. In addition, in real-world scenarios like in-memory key-value stores, abstract data can take the majority of the data structure's memory usage, which makes this strategy a preferable way to use NVM since it tends to be much larger than DRAM. But please note that abstract data is just the minimum set of information to be put into persistent payloads. Montage users can always persist more data for faster recovery after crashes. This is an example of Montage persistent mapping implemented as a tree. The dark blue blocks represents persistent payloads containing abstraction-related information. With only those blocks after crashes, the upper transient indexing structure can be rebuilt. For data structures like queues and graphs, it is tempting to have persistent pointers as a part of abstract data, which may result in persistent chains of unbounded length. This can be troublesome because if one block is updated for the first time in a new epoch, it will be done out of place on a new copy with a new address. Then all persistent blocks pointing at it will need to be updated as well, and they may also need new copies. This chain reaction can potentially propagate to the whole data structure. To mitigate this, we can use sequence numbers instead of pointers to record the order of queue nodes. A more general approach for graphs is using relation nodes with multiple pointers pointing to the source and destination of original pointers so that the maximum chain length will be 2. Montage is also suitable for non-blocking data structures. The challenge, in short, is that comparing to lock-based operations, it is harder to guarantee non-blocking operations to linearize in the epochs they're assigned with. In non-blocking data structures, write operations need to be assigned epoch numbers prior to their linearization point. Meanwhile, epoch advance and further write operations in new epoch may happen concurrently, causing operations marked with older epoch linearize in a new epoch. So if we want a non-blocking operation to linearize in a specific epoch, operations need to be aware of the epoch they should be in and to fail its linearization if the actual epoch is newer. To achieve this, Montage needs to identify all possible linearization points of all operations and make them epoch aware. If all data structure operations linearize on a double-wide counted cas instruction, we can verify the epoch counter between the cas and the previous read. By doing this, readers are made visible to writers so that writers in an older epoch can never be linearized after a reader in a newer epoch. If good performance depends on invisible readers, we can use a software double compare and single swap or hardware transactional memory instead. This way, writers can check the current epoch number and try to linearize atomically without readers doing any updates. Currently, we have implemented a verified cas interface in our codebase. With these efforts, montage-based non-blocking data structures are non-blocking in the online phase, but their persistence are still blocking because epoch advances wait for operations to finish and persist. We're now working on non-blocking epoch advance, with which a montage-based non-blocking data structure will become fully non-blocking. Montage prototype is built on Ralloc for fast NVM allocations and deallocations. In our current implementation, Montage provides a set of C++ API to track the reads and writes of persistent payloads. Montage may choose to apply the writes in place if the node is last updated in the current epoch, or create new nodes for the first update in the current epoch to preserve history. Either way, writes are registered with the epoch in which they are performed. Montage also tracks the boundaries of each operation in order to assign the same epoch number to all writes in the same operation. Recall that cache lines of each registered write in epoch E must finish writing back to NVM by the end of E+1, but the invocation of writes back can be as early as immediately after the write. The problem with that is on current Intel machines that supports Optane DRAM, CLWB instruction actually invalidates the cache line, which messes up the cache locality and degrades the performance of data structures. Another extreme is to delay writes back as much as possible, but that brings extra overhead of dynamic containers, and the writes back of each epoch may take longer than the desired epoch length itself, causing the epochs to grow exponentially. So our implementation uses small fixed-sized circular buffer or hash sets to delay writes back just enough to keep good cache locality, while the overhead of accessing and cleaning the buffer for an epoch is minimal. Besides writes back, payload reclamations need to be buffered for at least 2 epochs, since they cannot be undone after a crash. And we need unbounded containers for this. Interestingly, it turns out that we only need to be persisted and to be reclaimed buffers for at most 4 epochs at any time. So we only ever need 4 sets of statically allocated containers, and we can reuse them over time. Normally, global epoch in Montage simultaneously advances every 1 to 10 milliseconds, depending on the configuration. We chose 10 milliseconds in our benchmarks since it gives optimal or close to optimal performance for all of our benchmarks. While different applications may have an optimal epoch length out of this range. But sometimes, application may want to wait until all previous operations are persisted before its next instruction, and Montage provides sync function for this purpose. Since epoch E gets persisted by the end of epoch E+1, sync called in epoch E simply asks for epoch to be advanced to E+2. Epoch advance is done by a single background thread. It wakes up when epoch timer is up or when someone calls sync. For each epoch advance, just before advancing from E to E+1, it does all memory reclamations from E-2, persist all not yet persisted writes from E-1, issues an sfence to wait for persist to finish, and advances the global epoch counter. While each sync caller waits for its goal to be met, Epoch Advancer repeats this process until all sync callers are satisfied and goes back to sleep. Currently, we choose to let the background thread do most of writes back and reclamations to ease the burden of worker threads in the hope to achieve higher throughput. We are still exploring different sync implementations to see the trade-off between sync latencies and throughput. To test the performance of Montage, we used a Linux machine with 2 sockets, 80 hyperthreads in total. The machine has 12 NVM DIMMs distributed in 2 sockets and mapped in DAX mode and interleaved into one namespace. Threads of applications get pinned first onto cores in the first socket, then hyperthreads in the same socket, and finally the second socket. This slide shows the throughput of Montage among other persistent or transient implementations of hash maps. Note that the y-axis is log-scaled. Montage has significantly better performance than all other persistent hash map implementations except Soft, which has a significant drawback that it keeps a copy of all data on DRAM, so the size of the hash map is bounded by DRAM capacity. This slide shows the performance of montage-based queue among other queue implementations on a single thread and different key value sizes. Montage queue beats the state-of-art approach by a big margin. And this slide shows the performance of Montage instrumented Memcached with YCSB-A workload, along with Memcached running on DRAM, and a version of Montage with no write-back and fence instructions for comparison. At its peak, Montage version has only 10 to 15% of overhead comparing to the DRAM version. For more information about experiment setups and results, please refer to the full version of the paper. To wrap up, Montage reduces the persistence overhead of recoverable data structures by reducing the cost of persist ordering and reducing the amount of persistent data. It is suitable for both lock-based and non-blocking data structures. In experiments, it shows unprecedented performance as a general system for building persistent recoverable data structures. This work was published as a brief announcement in DISC 2021. The full version of the paper is available on arXiv, and the code is open source on GitHub. We're currently working on non-blocking Epoch Advanced and would like to explore atomic composition of operations on multiple data structures based on Montage. Thank you.